Hey everybody, I'm going to make a short lecture today on balancing chemical equations. I'm actually going to make this in a series of steps, so from pretty basic on to more challenging problems, all right? And I'll give you feedback in terms of where it might be a good point to stop and go do a bunch of practice, and then where to come back. We get into balancing chemical equations in chemistry. It seems like a strange topic. We kind of finished talking about how to write a chemical formula, and then all of a sudden we jump into this thing called balancing chemical equations. What's really going on here is the formulas that we're writing, these represent specific compounds, ionic compounds, covalent compounds. And these compounds can actually react with each other in a chemical reaction to produce new compounds. So a chemical equation represents essentially a recipe for how one or more compounds might come together to form one or more products. Okay, so essentially a chemical reaction is nothing more than a recipe, what I like to call a chemical recipe. And you might have a 3x5 box of 3x5 cards in your kitchen with recipes on them. And this is a recipe for pizza dough that I found somewhere, and it's got ingredients, and chemical reactions also have ingredients. And it's understood that these ingredients, water and yeast and sugar and flour and salt and olive oil, when they chemically react, they are going to produce a product, which is the pizza dough. So if you get this analogy that a food recipe, right, can produce a product, then you understand intuitively how a chemical reaction, ingredients, can produce products. So let me show you what this looks like. Okay, so what we've got here is a pretty basic chemical equation. And every single chemical equation actually tells you a lot of information, but it's in a very condensed form. Everything on the left-hand side, everything to the left of the arrow, is essentially an ingredient in this process. Now, chemists use a more technical term than ingredient, but if you know what an ingredient is, it's essentially what this word means. That the other word they use for this is reactant. And it's a little bit easier to learn ingredients before you learn reactants, just because of the terminology. Okay, then the arrow is a little bit tricky. The arrow obviously indicates the direction that the reaction is going to take. That's a very important consideration. If you stay into chemistry a little bit longer, maybe you take chemistry in college or take the second semester of chemistry, you start getting into reactions that don't necessarily go one direction, or reactions that go in multiple directions, so-called equilibrium reactions. So this reaction only goes one way without a substantial input of energy. If you were to turn this reaction around, it would require a substantial input of energy to move the reaction in the opposite direction. So we assume that everything we have on the ingredient or reactant side is essentially where we are starting with. And during the reaction, maybe you need a kickstart of energy, maybe you need to input some energy to get the reaction to start. At the end, you are going to end up with something that we simply call a product. Now, in this chemical reaction, we are taking hydrogen and oxygen, and you notice it's not just H and O, it's actually H2 and O2. And that's simply because that's the way hydrogen and oxygen are found, packaged together, at least in this universe, right? The way we understand how hydrogen and oxygen and other diatomic molecules like them, the way we understand them to behave is they're far too reactive to be alone, so they actually react with each other because they have a deficiency in terms of the number of valence electrons they have. So without getting too far into the idea behind the covalent bonding that occurs here, simply one hydrogen atom shares a valence electron with another and forms a bond. So there's actually two hydrogen atoms here. In this case with oxygen, it's a little bit more complex. Each oxygen atom shares two valence electrons with the other oxygen atom. So we understand that these represent, there's actually 4 atoms to start with. It's not just one hydrogen atom and one oxygen atom. Now we could say this, we could say that one H2 represents something we call an H2 molecule. So one H2 is really the same as one, the way we would say this is a one hydrogen molecule. And a molecule is a really small cluster of atoms that typically don't connect to other similar clusters. So an H2 would be a hydrogen molecule, and the same thing with O2. O2 would be an oxygen molecule. And during this chemical reaction, these atoms somehow, they seem like they end up combining together somehow, and they form a new molecule, H2O2, which you might know as hydrogen peroxide. So at the simplest level, if you had one single molecule, if you could reach into a jar of hydrogen and pull out one single molecule of H2 and one molecule of O2, and you have the sufficient amount of energy to get this reaction to start, you could make one molecule of H2O2. Now, you could only do that theoretically because, well, molecules are far too small to actually grab individual molecules. But this represents a recipe. And it is more than that. It represents a chemical equation. Now, there's more on this subject that we're going to talk about regarding chemical equations, and specifically the concept of the law of conservation of matter. We'll get to that in just a minute. But this chemical equation tells us a lot of things. The one thing that's obviously not written down is how do these atoms, hydrogen atoms and oxygen atoms, combine with each other? Do they just kind of fall next to each other and stick to each other? So this is one of the unwritten things in a chemical reaction, and it's kind of the essence of a chemical reaction. The idea that in any chemical reaction, bonds are going to break and new bonds are going to form. So suffice it to say, the bonds between all these hydrogen atoms are going to break, the bonds between these oxygen atoms are going to break, and we are going to make new connections or new bonds between the hydrogen and oxygen atoms. So it is just a coincidence that the formula we end up with has exactly the same ratio of ingredients. But it's not always that way. Sometimes you need more of a specific ingredient to make a certain amount of product. So a simplistic way of envisioning this at the end is that hydrogen peroxide is going to have hydrogens connected to an oxygen, connected to an oxygen, connected to a hydrogen. And the only way this can happen is if the original bonds between hydrogen atoms, this bond is somehow severed, and the bond between the oxygen atoms themselves are also severed to make our new product. Okay, so this is every bit a recipe as you would have for making pizza. Now what's interesting is using these starting ingredients, this is the only hydrogen peroxide, the way you can make, I'll say this is the only way you can make hydrogen peroxide using these two individual ingredients. It is not, however, the only product you can make using these two ingredients. In fact, you can make water using these two ingredients, and that might be a much more common process to make than making hydrogen peroxide. But I wanted to start here. Okay, so there's one thing you really want to notice, right? And I'm going to clean this page up just in a second. So the one thing we want to take note of is there's a really important concept in chemistry, and I'm just going to kind of go to that concept right now. It's called the law of conservation of matter. And just if you've taken a physics class, you've heard of other conservation laws, like the law of conservation of energy, the law of conservation of momentum, or even angular momentum. There's a law of conservation of matter in chemistry. And the basic idea is that in any chemical reaction, lighting a match, putting metal in acid, the rusting of metal, even something like cellular respiration or photosynthesis, any type of chemical reaction, matter cannot be destroyed. And what I mean by that is really atoms cannot be destroyed, but they also cannot be created in the course of a reaction. So if I start a reaction with, let's say, 2 oxygen atoms, what that means is I have to end up with 2 oxygen atoms. I can't eliminate an oxygen atom. I can't destroy an oxygen atom. I can't make a new atom. I can't start a reaction with copper and end up with lead. So now there's a slight tangent to that, because in nuclear reactions, you can turn one atom into another atom. With alpha decay, you can turn uranium into thorium. And with beta decay, you can turn carbon-14 into nitrogen-14. Well, that's not what we're talking about here in a chemical reaction, okay? So the basis of any chemical reaction is that atoms have to break their connections with each other. A more technical term for connections is this word bond, and there's multiple types of bonds atoms can have: metallic, ionic, covalent bonds. And they have to make new bonds. That's it. That's the only thing that happens in a chemical reaction. So matter cannot be created or destroyed in this process. So let's go back to our hydrogen peroxide reaction. So what we normally have people do to prove to you that matter is not destroyed is take an inventory, right? One of the things we task students with is balancing a chemical reaction. And the idea is that we need the chemical reaction to obey the law of conservation of matter. So I say, you just kind of take an inventory, right? So I'm going to take an inventory. I'm going to write this down. Whoops, have a little problem there. So I'm going to take a little inventory of the atoms the atoms that I have at the beginning, the atoms that I have at the end. Well, it looks like I have hydrogen atoms to begin with, and I have oxygen atoms to begin with, and I end with hydrogen atoms, and I end with oxygen atoms. So that's good. I'm not creating copper. I'm not doing anything strange. Now, how many hydrogen atoms do you start with? Well, the subscript 2 tells me I start with 2 hydrogen atoms. I'll just put a 2 here. The subscript after the oxygen says I start with two oxygen atoms. It's good. In the end, the subscript 2 after the hydrogen tells me I end with 2 hydrogen atoms, and I end with 2 oxygen atoms. And this is exactly how it should be in what we would call a balanced chemical equation. I start with 2 hydrogens, I end with 2 hydrogens. I start with 2 oxygens, I end with 2 oxygens. This is a balanced chemical equation, okay? All right, now, one of the things I said a few moments ago is the idea that hydrogen peroxide is not the only chemical you can make using these 2 starting ingredients. So we said you could actually make water. Let's take a look at that. So a more common reaction you might make with these 2 starting ingredients is actually water. Only this time, our recipe for making water has a problem. So let's investigate this by taking an inventory. So I look at what I have to start with, and I should have exactly the same number of those atoms that I end up with. So I start with hydrogen, and I start with oxygen, and I end with hydrogen and oxygen. That's pretty easy to see. Well, how many atoms of hydrogen do I start with? I have 2, and I have 2 here. That's very similar to the problem we did a minute ago. And this 2 is for the hydrogen. Yep, so I end up with 2 hydrogen atoms, but oxygen does not have a subscript. In the chemistry, if something does not have a subscript, that means 1. So I end with 1 oxygen atom. So as a whole, this chemical equation, as it's written, does not obey the law of conservation of matter, because somehow it ends up destroying an oxygen atom in the process. So this is something that simply can't happen. So we need to figure out a way to, how would I end up using this extra oxygen atom that's left over at the end of the reaction instead of having it left alone. So there's a couple things that you can't do. In order to get a second oxygen atom over here, I can't modify the chemical formula, because as you may know, water is not the same thing as hydrogen peroxide. So we can never modify the chemical formula. I also can't just add an oxygen to force it to work. Again, oxygen on its own is an incredibly reactive substance. It's just never found in nature. So I also can't do this, right? So the only way that looks like we can get more oxygen on this side is to add more of the compound that the oxygen is connected to. And in order to get 2 oxygens on this side, it looks like the only way to do it is to add more waters. So this represents 1 water molecule, Well, the only other way to get another oxygen here is to add another water molecule, right? That would certainly be a way to use up both of these oxygens, and that does make it so I start with 2 oxygen atoms here, and I end with 2 oxygen atoms here. But you may notice in this process, we're not done yet, because in this process of adding an extra water molecule, I've also doubled the amount of hydrogen I end up with. 2 hydrogens here, 2 hydrogens here. That gives me 4 hydrogens. So how would I fix this? That would mean if I end up with 4 hydrogens, I'd have to start with 4 hydrogens. So the only way to get more hydrogens, and again, the same reason I can't change this formula to an H4, I can't modify it. The only thing I could do is add more H2s. I need more H2 molecules, right? So if I had a total of 2 H2 molecules, so H2 plus H2, that would definitely get me 4 hydrogens. And now my formula is balanced, right? So I'll even write in the word balanced. So balanced, we're good, smiley face, except, well, you can simplify this, right? In chemistry, instead of saying H2 plus H2, we figure out that, well, the easier way to write this is to not write both of them in, but instead use a coefficient. So I will change colors here, and I will add a coefficient of 2. So the 2 in front of the H2 really says that I have 2 molecules of H2. And 2 molecules of H2 are going to have 4 hydrogen atoms. So it may take a while to get used to the idea of what a molecule is. So the 2 in front means exactly the same thing as having H2 plus H2 is what I had before. And for the same thing, I could do exactly the same thing on the other side. Instead of writing H2O plus H2O, I can simplify this, and I can instead put a coefficient of 2 in front, because the 2 in front of the H2O represents 2 molecules of water. And 2 molecules of water are going to have 4 hydrogen atoms and 2 oxygen atoms. Okay? And now our equation is balanced. So this is the process to balance a chemical equation. Take an inventory, and you can modify the ingredients or products as necessary, so you end up with the same number of atoms to beginning and to end, right? So I start with 4 hydrogens, I end with 4 hydrogens. I start with 2 oxygens, I end with 2 oxygens. So in a cooking or baking reference, another way to view the coefficient is like the number of cups of ingredients you might need. So it says I need 2 cups of hydrogen and 1 cup of oxygen. And in the end, after I bake those, with baking in quotes, I can make 2 batches of water, right? So thinking about this in terms of a baking reference can really help. All right, let's try another one. It may be a little bit more advanced. So here's another chemical equation. This is a chemical equation for the decomposition of this substance called potassium chlorate. It decomposes to form potassium chloride and oxygen. And it's not balanced. So let's take an inventory. Before the reaction starts, I have potassium. Cl is not 2 atoms, it's 1 atom, chlorine, and I have oxygen. And let's see, do I end up with the same atoms? Yes, potassium, chlorine, and oxygen. So if I study the subscripts for potassium and chlorine here, you notice they're both 1s. There are none there, so that means 1s rather. So I have 1 of each of those atoms, and I have 3 oxygens. Remember, the 3 does not apply to the chlorine or the potassium. If it did, the formula would be K3Cl3O3. On the other side, I have 1 potassium and 1 chlorine, but 2 oxygens. So, okay, obviously we're not balanced. The oxygens are not balanced. Now, again, I can't fix this by changing the oxygen to an O3. O3 is ozone. It is not the same substance as oxygen. The only way is to get more oxygen here, but you see we're in a bit of a pickle because we have this even-odd situation. So when you have an even-odd situation, I kind of recommend lowest common multiple. And the lowest common multiple between 3 and 2 is 6. So I really want to get 6 oxygen atoms over here. So I can do that by having, if I had three oxygen molecules, that's the same as having 3 times 2, or 6 oxygen atoms. And to get 6 oxygen atoms in potassium chlorate, I'd really need 2 of them. I'd need 2 molecules of potassium chlorate. 2 times 3 gets me 6 oxygen atoms. And so far, we're good, but by adding a 2 in front of the potassium chlorate, it changes the number of potassiums and chlorines. Now I have 2 potassiums and 2 chlorines. And, well, I need to get 2 potassiums and 2 chlorines here. So I can modify that by having a second potassium chloride molecule. 2 and 2, and now we're balanced. Okay, so at this point, you should stop. And you should go balance a bunch of chemical reactions. And until you get to the point where you understand how to do it well enough that you do not need to make an inventory every single time, right? So after you've balanced those problems, come on back. I'm going to show you a little bit harder problem. Okay, so if you're back and you want a little bit more, now we've got something a little bit more difficult. Now I've got a chemical equation, but it's written as a word problem, okay? So now I would actually have to work backwards and figure out what these formulas are first before I then go and write a chemical equation. So if we kind of tackle this problem, I can tell where my ingredients are. It looks like my ingredients are lead-2 nitrate and sodium chloride because it says reacts to form. So I'm assuming that these are my ingredients. My arrow is here. My products are sodium nitrate and lead-2 chloride. So remember the Roman numeral 2 is there for transition metals to tell you what the charge of that ion is. So lead is going to form a +2 charge. Nitrate is NO3 is a -1. So if I combine those two, a +2 and a -1, well, I'm going to need 2 -1s to offset the +2. So this is Pb parentheses NO3 n parentheses 2 plus sodium chloride. Well, most people remember that sodium will form a +1 charge if it forms a compound. Chlorine will form a -1 charge if it forms an ionic compound. So I'll form NaCl and then an arrow, sodium nitrate. So you might also notice that this is a double replacement reaction. So really what's really happening here is the lead is swapping places with the chlorine. So I'm going to make sodium nitrate. Again, sodium does not change its charge. In an ionic compound, it's +1, and nitrate is always NO3 -1. So I only need one of each to offset each other. NaNO3 plus our last compound, lead-2 chloride. Lead-2 is obviously lead Pb +2, and chloride is the Cl -1 ion. So I have PbCl2. And it is not balanced yet. So at this point, now that we have the chemical equation, now we can go back and balance it. So it looks like to balance this appropriately, I guess I'm going to choose red right now. I have 2 chlorines here, so I need to start with 2 chlorines. So another way of balancing the equation is just to kind of balance it on the fly. Most people get to this point after they've balanced 5 to 10 problems. They kind of get the process. So to get 2 chlorines on the ingredient side, I have to put a coefficient 2 in front of the sodium chloride. When I put the coefficient 2 in front of sodium chloride, it gives me 2 sodiums. I only have 1 sodium on the product side, so I need a coefficient 2 in front of here as well. And that fixes the sodiums and the chlorines, but the nitrates, now I have 2 nitrates, and I have 2 nitrates over here. So the equation is balanced. So this process is a little bit harder, right? Because you have to take a word formula, lead-2 nitrate, and turn it into a chemical formula, and then write a balanced chemical equation. Okay, balancing is, I'm almost finished, but balancing is something that can only be done with trial and error, right? Let me do one more problem, right? I'll kind of show one more problem on balancing. This one's fairly challenging, all right? So take something like, how about C8H18, that's octane, and I'm going to combust it with oxygen to make carbon dioxide plus water. Now I want to try to balance this on the fly, all right? So I see I have 8 carbons to start with, so I figure I'm going to try and put 8 here. That'll fix my carbons, and then I have 18 hydrogens. Well, to get 18 hydrogens over here, I'd have to put a 9. And so far my carbons and hydrogens are fixed, but I need to really fix my oxygens. I have 8 times 2, 16 oxygens from here, and 9 times 1 and 9 oxygens here. That gives me 25 oxygens total. Well, there's no way to get 25 oxygens out of O2. So what do? Well, you got to start over, right? It means all the work that you just did is incorrect. So let me erase all this. This is not correct. Sometimes when you end up with something that's incorrect like this, obviously the problem is that I ended up with an odd number of oxygens. So the only way to really get more oxygens is to double the amount of starting ingredients I have. So I'm going to go over here and basically, let's say if I doubled the amount of octane that I have. Now I've got 16 carbons. Well, I can fix that on the product side by putting a 16 in front. And I have 2 times 18, or 36 oxygens. So to get 36 oxygens, hold on a second. I need 18. I don't know why I just had a mental block. So I'd really need to have 18 waters to get 36 hydrogens, right? 2 times 18 is 36. 18 times 2 is 36. Now if I come to sum my oxygens, now I have 16 times 2. That's 32 oxygens. Here I have 18 times 1. That's 18. And if I sum these now, 32 and 18 gets me 50 oxygens. That's something I can work with. How do I get 50 oxygens here? 50 oxygen atoms, well, I'd really need to have 25 oxygen molecules. Now your equation is balanced. It's tricky. It takes time. You really do have to put in the time on balancing equations to really get comfortable with it. And that's it. So remember, at the end of the day, all chemical equations have to obey the law of conservation of matter. And that is our ticket out of here. All right, so go practice balancing. Have a great day, everybody.